There are several types of substrate one can use for producing Beauveria metarhizium cordyceps fungi. Of course, the standard in many countries is rice. Here we have some long grain culinary rice. There are different varieties of rice, and they will require a slightly different hydration and autoclaving methods. So in addition, one can often obtain broken rice. And here you see the rice is broken into small pieces. The advantage is that there is a greater surface to volume ratio. In other words, more surface area per gram of substrate, which can produce a greater number of aerial conidia. This oftentimes is a waste product. In North America, this is actually a premium price product, much more expensive than regular rice, so it is not used. In North America and in Europe, what is most commonly used is a flaked cereal, such as wheat, barley, or oats. What you see here is that the outer layer is stripped off, and in addition, the grain is flaked, so that it is much more absorbent of water and also more readily colonized by fungal mycelium. This is really the substrate of choice in North America and in Europe. In addition, flaked barley is used as an animal feed, so that it is actually much lower cost than even rice is in the United States and Canada, for example. Next, we have hulled millet. This is hulled, so the outer layer is removed, making the millet much more water absorbent. Millet, again, is a large surface area to volume ratio, but also the spent millet can be used as a granular formulation for application into the soil, where the mycelium colonizes the millet, and then after the spores are removed, the mycelium is preserved inside the millet. When it is rehydrated, for example, by application to soil, the fungus grows out and resporulates. So this is an advantage, and this is currently a commercial substrate that's used in South Korea. Lastly, I will mention an inert substrate. It's diatomaceous earth that is granulated. And the advantage of this is that it can absorb whatever liquid medium is optimal for conidial production of your fungal species and strain. In North America, it's obtainable as a material to absorb spilled motor oil and other lubricants, as well as liquid spills, and it is very cheap. The advantage of this inert substrate is that once it is used, it can be washed and reused again on autoclaving. As a demonstration of preparing substrate for autoclaving, in this case broken rice, I'll be using small scale. This is suitable for laboratory use in evaluating spore production by strains of a fungus to optimize moisture levels in substrate and so on. And for this purpose today, I'm using these small mushroom spawn bags with a vent for good aeration. I realize that this is probably not economically suitable for mass production, especially in Southeast Asia. But the key point behind these bags is that the fungus culture on whatever substrate has ample ability to have gas exchange, because the fermentation requires a lot of oxygen, and CO2 must be given off and removed from the environment of the fermentation. So simply for preparing the substrate, the first step is to hydrate it. The hydration with rice is typically 50% water. In other words, 500 milliliters of water for every kilogram of rice. And so for today, I am just simply going to be weighing out 200-gram amounts of broken rice. So we have 400 grams of rice. So for 50% hydration, we are needing 200 milliliters of deionized water. Do not use tap water because chlorine residues can influence the subsequent fermentation. At a minimum, you should use reverse osmosis water. Highly purified distilled water is not really necessary. Reverse osmosis water is suitable. So we simply add the water to the rice and we mix. And then we let the rice sit for 30 minutes. I'm also going to demonstrate preparation of a flaked barley as a substrate. Again, this is the favored substrate in North America and Europe, and you'll see why in a moment. So again, I'm preparing 2 batches of 200 grams of the flaked barley for 200 grams going into each spawn bag, as I showed you before. So the first step again is to weigh out. So that's 200 grams of barley. And now I'll weigh out the second 200 grams of barley. Again, if you're doing solid substrate fermentation to determine yields of candidate strains, you want to be fairly accurate in how much dry rice or barley that you use, and also the levels of hydration. For these flaked cereal grains, 50% water is, again, the optimum. One can go 55%, maybe 60%, but not 40% moisture. So in this case, it's simply adding 200 milliliters of water for 400 grams of barley and quickly mixing it. And if in the case of these cereal grains, you want to mix very well and very quickly and vigorously because the barley rapidly absorbs whatever more water it is offered. You can see how rapidly the flaked cereal grain absorbed the water. So no additional incubation is necessary. At this point, the moistened cereal grain, again, this is barley, can be transferred into the spawn bags for autoclaving. This rapid hydration is another aspect favoring the use of flaked cereal grains in the United States, such as at Certus in Butte, Montana, where the production levels are on the range of tons of substrate each fermentation batch. With the barley, we want to transfer the appropriate amount of barley into each fermentation sack. In this case, each batch is 200 grams dry barley plus 100 milliliters of water for a total weight of about 300 grams. So again, to be precise for yield determinations for experimental purposes, I'm going to be weighing out 300 grams of wet barley. And it is easier to actually put the fermentation sac, whether it's a spawn bag like this or a regular plastic bag, directly in some sort of holding container, re-tear the balance, and then simply add sufficient barley to reach the 300-gram mark. In making multiple batches, it is often more efficient to weigh out the total amount of grain, whether it's rice or cereal grain, and mix it all together in one, rather than to add the dry barley into a spawn bag, a plastic bag, and adding the appropriate amount of water. Also, it's very valuable to be able to mix the barley for even hydration. Simply adding water to the dry barley in a bag and then mixing it doesn't give you good homogeneous distribution of the water. So this is one bag ready to be prepared. I'm going to be filling the second bag now for today's demonstration. Again, what should be remaining is 300 grams of moistened barley. In scaling this sort of system up, one can possibly use machinery that will automatically dispense a certain amount of moistened grain, whether it's rice or barley, into a whole series of bags, and thus be mechanized. Again, what I'm demonstrating today is simply small-scale production for use in a laboratory and to demonstrate the basic methodology. Okay, so now that we have the barley transferred into the bags, we must close the bags up for autoclaving. In the case of these type of bags, all we need to do is fold over several times. In my case, I have to make these small bags because of the limitations of my autoclave. But simply do some sort of clipping such as this. And this bag is ready for autoclaving. Again, we just fold over. With non-vented bags, basically all we have to do is use a rubber band or some closure and autoclave them like this. And you'll notice here with these vented bags, I have folded it over so that the steam can actually penetrate down into the moistened barley and sterilize it. Autoclavable plastic bags are the most commonly used in Latin America for production, containing 100 or maybe 200 grams of rice. So this is one kind of bag. Now, it's very important that the fermentation is allowed to breathe, and yet contamination is excluded. And one way to do that, the simplest way, is simply to close the bag off and put in a temporary clip to keep it closed, doing this in a sterile environment, such as a laminar flow hood, and then letting the fermentation run like this. There's enough gas exchange if this is kept loose. You do not want to make a very tight closure here, because what you're doing is you're preventing gas exchange and, in a sense, asphyxiating the fungus that's growing on whatever substrate that you're using. So failing or an alternative to this loose closure, which does render the bag potentially susceptible to some contamination if you're working in a heavily contaminated environment. So an alternative to this is to make a small sleeve out of some autoclavable plastic. In this case, for this example, I'm just using paper, and creating a plastic flask, if you will, that you then use with a cotton stopper. And you then have the fermentation that can breathe. You want this sleeve to be light. One could possibly use a PVC joint that's used in plumbing, but oftentimes that's heavy and will cause the bag to flop over. So you want a light plastic sleeve. You could scale this up to a larger bag for 1 kilo of substrate, but for the purposes of this short course, I can't demonstrate that. What is often used in more advanced technology are mushroom spawn bags, such as this one here, which has a microporous vent. There's all sorts of sizes and shapes. Here is one that is actually this, which I've modified, but this is the original bag for growing agaricus spawn. Again, with a good vent. The vent is a 0.2 microns pore size, so it excludes microorganism contamination. It allows for good gas exchange. A larger version is this spawn bag with a very large Tyvek strip, again 0.5 or 0.2 micron pore size, and this one can hold up to 500 grams of rice. The deluxe version is these spawn bags from Europe. These are the vents, and they're ostensibly designed for agaricus production. But however, I have used these successfully for up to 2 kilograms of substrate for growing Metarhizium and Bavaria. However, these are expensive, so and they can be only obtained from this one company that's in Belgium. So that's a disadvantage. One can actually even use these shopping bags. These are generally autoclavable. You want to get one that's a little thicker than this grocery shopping bag, and you want to use them fresh. You don't want to use a recycled bag because that will have holes. But it is quite feasible to take this bag, modify it a little bit, and you now have an autoclavable plastic bag that can hold 200, 300, maybe 500 grams of rice in the substrate, much like one of these. So there's a variety of bags. Okay. Now, after about half hour, you can see the rice has absorbed the moisture, and it is evenly moistened and now ready for transfer into the spawn bag. Again, for this particular example, we're using these bags and 200 grams of dry rice, 100 grams of water, so that's a total of 300 grams of wet rice go into each one of these bags. And to do that, I simply transfer the rice into a tiered bag and container. Again, for yield purposes, for yield calculations, you want to be fairly precise in the amount. So for example, here I am doing 300 grams per bag. You'll see that there is still some water that hasn't been absorbed. This will be absorbed when the substrate is autoclaved within its bag. Okay, now that the rice is transferred over into each bag, we have to close the bag, but not tightly. If you were to heat seal the open end of the bag and autoclave it, the bag will explode in most cases. So you want to be able to allow steam to go in and out of the bag. And in this case, we're using these light closures. When you're folding these bags, it is best not to have too much head space. So you have something like this for autoclaving. Now we want to have our bags of rice and barley autoclaved. And for my purposes, with my autoclave, I will arrange them like this. You want to keep the thickness of the substrate no more than 2-3 centimeters in depth, so that the steam readily penetrates the entire mass of substrate. Again, so with the barley, this was the barley that we hydrated, so they get laid ideally on a flat surface. One of the biggest problems with insufficient autoclaving of substrate is to have an ample volume area around each bag so that the steam can percolate. One of the easiest ways to get insufficient sterilization is to arrange the bags in an autoclave in a tightly packed mass like this. The result will be that in the center here you will get insufficient sterilization, and the existing contamination will then overwhelm the Beauveria metarhizium cordyceps fermentation. So you want to be able to space. If you're autoclaving bags on a vertical, you need to put a spacing between the two bags. So again, in sterilizing by steam, you want to make sure that there's plenty of space around the bags so that it reaches all through the bag fermentations. And so here in this example with this autoclave, we can do 6, maybe 9 bags at a time. And again, I'm leaving these vents open so that they are exposed so the steam can penetrate down through the vent and sterilize the substrate. When you're sterilizing substrate, it is very beneficial to take one extra bag and insert into it a sterilization indicator. And this is inserted into the center of the substrate. Obviously, this bag cannot be used for fermentation, but it is very valuable to monitor the extent and the completeness of the steam sterilization process. This is, again, one aspect of the quality control on preparing substrate. Even in doing large batches, let's say 100 bags, you want to have one bag at least with one of these, and to sacrifice the bag when you remove this, but it'll be an indicator that you're getting proper sterilization. Ideally, you should use a liquid medium to produce inoculum for solid substrate. Contrary to what many of us believe, you do not need a shake flask type of fermentation. It's just as easy to use a magnetic spin bar fermentation, either in small flasks. For example, this is enough inoculum for 500 grams of solid substrate. So for a small scale in a laboratory, this is ideal. And here we have two different media. This here is a glucose yeast extract, potassium nitrate, potassium phosphate medium that is ideal for Bovaria, preparation of Bovaria inoculum. This is a yeast extract glucose medium that is ideal for producing Metarhizium species, or also this one can be used for Eiseria, the cordyceps fungus. As you see here, these are sample, typically how I do this in my lab for small experimental formulations of fermentations. This here again is 50 milliliters, which is enough for 500 grams of solid substrate. Again, for evaluating yields of candidate strains and so on. It can be scaled up. So, for example, this is 900 milliliters of medium with a magnetic stir bar in the bottom. A cotton stopper for good aeration. This is sufficient for treating, inoculating 9 kilograms of solid substrate. A magnetic stir plate is more than sufficient in providing the agitation needed for good aeration of a liquid pre-culture. The volume can be scaled up. This is 900 milliliters of liquid medium, and the magnetic stir bar is providing more than enough agitation for good aeration of the liquid pre-culture. So alternatively, one can use these type of spin flasks, which have volumes up to 5 liters for producing liquid inoculum. We are now going to demonstrate inoculation of the liquid medium under aseptic conditions. First, of course, we have to sterilize the work surface. Ideally, this should be conducted inside a laminar flow hood or biohazard hood to maintain aseptic conditions. Then the gloves are not sterile, so they must be also sterilized with a little alcohol and for rubbing. So here is our initial source culture. This is a Metarhizium anisoplii, and we're going to use this to inoculate some of the Metarhizium medium that I indicated earlier. Very simply, one takes aseptically a cotton swab, loads it with Canidia, and transfers that to the flask. One could also do a second amount. You see how much Metarhizium I have on there. And that's sufficient for inoculating the liquid culture. Now I'm going to inoculate the glucose, yeast extract, potassium nitrate medium that's ideal for Beauveria production. And again, following the same method. Take a sterile cotton swab, load the tip of the swab with spores, as you see here, and place them into the liquid flask. These volumes of 50 milliliters are ideal for small fermentation quantities, let's say multiple bags of 100 grams of substrate, or they can be used themselves as inoculum for larger volumes of liquid medium that would subsequently be used to inoculate larger quantities, kilogram quantities of solid substrate. In order to maintain the integrity of candidate isolates of Beauveria metarhizium you obtain, you have to do long-term preservation. And for that purpose, suspension of spores in 10 to 30% glycerol and freezing at -25 to -80 centigrade is ideal. Advantage of using 30% glycerol over 10% glycerol is that at -25 storage, which is the typical normal freezer, the suspension is still liquid. And as you will see subsequently, it's easier to transfer a bit of inoculum from that glycerol solution to an agar plate without thawing the suspension. Typically, these preserved cultures are done in microcentrifuge tubes, such as this, which have been previously sterilized. Alternatively, one can use tubes such as this, which are screw cap freezer tubes, especially for storage at -80 degrees. These are more than sufficient for -25 degrees. The typical technique, again, is to take a sterile microcentrifuge tube, label it properly, and prepare it to receive some inoculum. Again, I am using 30% glycerol and transferring that with a sterile plastic transfer tube. Again, this should be done in a laminar flow hood to maintain aseptic conditions. The technique is to fill the tube up about halfway with the glycerol. And then to use a sterile cotton swab that has been immersed in the glycerol to pick up a large quantity of spores. Then that's inserted into the microcentrifuge tube, and the cotton swab acts as a mortar and pestle to thoroughly suspend the spores up in suspension, as you see here. One can add some more spores with a second quantity. And again, twist with the cotton swab to wet the spores and get them thoroughly in suspension. Ordinarily, the spores are difficult to suspend. However, this method here really facilitates the suspension. Once the spores are suspended, additional glycerol is added to the centrifuge tube so that it is almost filled. And then it can be capped, shaken some more to mix the spores in, and then the microcentrifuge tube can be added to the appropriate container and frozen away.